And here we go. All right, this is the instructional YouTube video for section 3.2, Precalculus. We're gonna start off with a bad joke in a British accent. So, I was talking to my mate and I was like, what does a Precalc student have in common with a recording studio? And they're like, I don't know. And I was like, they both know how to logarithm. Get it? Logarithm. Okay, so that was my bad joke in a British accent for the day. I'll try to keep those coming because, well, you might not like them, but I do. So our learning targets today are evaluating just simple logarithms and graphing logarithmic functions and just looking at some basic properties of logarithms. So remember, all right, we talked about this. F of x equals log base b of x is the inverse function to g of x equals b to the x. Right, those are inverses. Right, they're inverse functions. If you were to graph one and graph the other, it'd be reflections over the line y equals x. And the definition of a logarithm is if we have log base b of a, this is the exact, equals x. If this equals some number, let's not call it x, let's call it n. Let's get rid of the x. This is the same information as a equals b to the n. And we can talk about why that's true. So we know that the b to the function and the log base b of function are inverses. So that means they undo each other. They're the opposites. So if I take this equation and I exponentiate both sides, b to the log base b is going to cancel out because they're inverses. So I get a equals b to the n. If I take this function and I take log base b of each side, the log base b of b to the n, that's going to cancel out, and you're just going to get the argument of the exponent. So this will give you log base b of a equals n. So it works either way. You can just undo it either way. So we're going to do some evaluating with logarithms just using these properties, or this property here. All right, we've got, let's say, log base 5 of x when x equals 25. That's how it looks in the homework. Log base 9 of 3, and then log base 3 of 1 over 27. All right, let's go through these. So for this one, what this means, we've got log base 5 of x when x is 25. It just means replace this x with a 25. So we're evaluating it log base 5 of 25. And let's just say this equals some number n, just like this. So we can just jump straight to the exponent form, or we can rewrite it in, or we can exponentiate each side by going 5 to the 5 to the, using that inverse operation or the inverse function of, the exponential function. So 5 to the log base 5 cancels out, so we get 25 equals 5 to the n. And now our goal is just like, hey, what number can I put in for my exponent? 5 to the what gives me 25? Well, we know 5 squared equals 25. So that means n equals 2. So this, log base 5 of 25 equals 2. All right, let's move on to this one here. We got log base 9 of 3. So once again, we can say this equals n. We can exponentiate each side. We're going to use a base of 9 this time. So basically, it's 3 equals 9 to the n. Like, ooh, what kind of exponent can I put in on the 9 to make that number smaller, but still a whole number? Well, in this case, remember a fraction exponent that's less than 1 is a root. So here, if I square root 9, I get 3. So in this case, 9 to the 1/2 equals 3, which is the square root of 9. So in this case, n equals 1/2. Or we could say right? Log base 9 of 3 equals 1/2. All right, log base 3 of 1 over 27. So same thing, 3 to the equals n, 3 to the, so this gives me 1 over 27 equals 3 to the n. We need to find what exponent, 3 to what exponent gives me 1 over 27. So here, it turns into a fraction. Really, this is 27. 27 is 3 times 3 times 3. It's 3 to the third. But because it's in the denominator, we're dividing by 3 times. So remember, positive exponents mean multiply, negative exponents mean divide. So this means 3 to the negative third is 1 over 27. So n equals negative 3, or we could just simply say log base 3 of 1 over 27 equals negative 3. Now notice, the answer to each of these is the value of the exponent with that base that gives you this number as an answer. So for example, 5 squared equals 25. So log base 5 of 25 equals 2, because 5 squared is 25. Log base 9 of 3 equals 1/2, because 9 to the 1/2 is 3. Log base 3 of 1 over 27 equals negative 3, because 3 to the negative 3 equals 1 over 27. Each of these answers represents the exponent number on this base to give you this as your final answer from your exponent. Hopefully that didn't confuse you more. All right, we're going to do some more examples. We're just going to run through some examples. Each of these examples is going to highlight a logarithm property. So, here we go. We're going to take the log of 1,000. Notice, I didn't write a base here. When there's no base given, it's just log. That's log base 10. We call it the common logarithm. So here, really, we have log base 10 of 1,000. So this is log base 10, the common logarithm of 10,000. And here we're like, well, 10,000, because remember, this answer is going to be 10 to the what power gives me 1,000. Well, 10 to the first is 10, 10 squared is 100, 10 to the third is 1,000, so the answer here is 3, because 10 to the third equals 1,000. And in general, if I have log base b of b to the whatever exponent, n, this is just going to be n. That is a logarithm property. Log base b of b to the n equals n. In other words, the log base b and the b to the function, or the log and the 10 to the function, log base 2 and the 2 to the, are going to cancel out, and you're just going to be left with whatever's in the exponent. All right, let's do another one. Let's say we have this. Well, here, this ln represents the natural logarithm. It's French, so it's ln instead of nl. But the natural logarithm, and the natural logarithm is the logarithm base e. So it's similar to log base 10 of 10,000. We have the log base e of e to the negative third. So using this property, where the base matches the base on the logarithm and the base on the exponent, this just gives us negative 3. The natural logarithm cancels out the e to the part, and we're just left with the argument of the e to the function, or the e to the whatever expression, the exponent. All right, and that's it. Let's say we have log base 3 of 3. Well, 3, this number 3, is 3 to the 1. And remember, the answer to these logarithm problems represents the exponent. That 3 to the what gives you 3. So this is just 3 to the 1 gives me 3. So the answer here is just 1. right? Because if I did 3 to the n equals 3, n would be 1. And in general, if I have log base b of b, it's 1. If these two numbers ever match up for the exact same number, your answer is 1. Okie dokie. Let's say we have, let's just change the color. Orange. Let's say we have log base 7 of 1. Well, here, right, let's work through this one a little bit. Let's say we've got, say this is n, we go 7 to the 1 equals 7 to the n. 7 to what power gives me 1? Well, in general, if we think back to our exponent rules, a non-zero number to the 0 power is always 1. So here, it's just 7 to the 0 equals 1. So log base 7 of 1 equals 0. And in general, log base b of 1 is 0. So no matter what that base is, assuming the base is a positive number, we don't do logs with negative bases. That'd be weird. Log base b of 1 is always going to be 0. All right. Let's say I've got this. 9 to the log base 9 of 8x plus 1. Well, here, this is the opposite of these two. We have 9 to the log base 9 of something. And remember, the log base b and the b to the are inverses. We have to have matching bases. We have matching bases. So the 9 to the and the log base 9 of, cancel out, and we're just left with the argument, whatever's inside the logarithm. So here, this just equals 8x plus 1. Now, we'll have to talk about, like, restricting the domain here, because we can't take the logarithm of any number. We'll talk about that in a bit. But in general, 9 to the log base 9 of stuff is just equal to the stuff on the inside. All right, let's look at log base 5 of 0 and log base 5 of negative 5. All right, I'm going to work through these the same way I worked through the log base 7 of 1. So I'm going to say this equals n. I'm going to go 5 to the, and I get 0 equals 5 to the n. Same thing here. Let's say this equals n. 5 to the, I get negative 5 equals 5 to the n. So right now you feel like, something's wrong here. Yeah, something's wrong here. Because if we look at the graph of 5 to the n, the graph of 5 to the n is going to look like this. 1, 5, right? 25's up there. As you go, woo, supersede. And then as we go to the left, we get this asymptote at y equals 0. In other words, y equals 5 to the x, or 5 to the n, whatever, is always going to have a positive answer. In other words, there's no number I can put in the exponent here to get 0 or a negative number, right? This graph is never going to hit 0, because that's our asymptote, and it's never going to go down here to negative 5. So both of these, we could either say undefined, that's what I'd go with, these are undefined, or maybe, depending on what the homework question's asking for, does not exist. All right. So in general, for a logarithm function, okay, where this is 1, 0, the domain for log base b of x is 0 to infinity. We can only take the logarithm of positive numbers bigger than 0. We can't take the log of 0, we can't take the log of negatives. Okay. And that's when there's no transformations happening here. Once we do some transformations on the logarithm function, right, then hey, that asymptote might move. We have to like shift it left 10. Well, then it's got to be bigger than negative 10 instead of bigger than 0. All right, we're going to do a little bit more work with the natural logarithm, because natural log and e to the are super important in calculus. You see them all the time. And here we go. And just a second, I'm looking at my camera right now, and it looks like I can't see the side there. It's good. Okay, cool. Just the angle on my camera, it looks like it's gonna cut it off right here. I just had to check. Sorry, you had a good view of my shirt pocket there. Okay, so I got natural log of 50 equals approximately, it doesn't equal, a decimal approximation of this is 3.912. And then e to the 6, let's say e to the negative 5 is approximately 0.0067. Let's rewrite these in their other forms. So rewrite in equivalent form. So here I want to write this as e to the something is about what? This one I want to write L natural log of something is about what? Well, here natural log, the inverse of the natural log is the e to the. So I'm going to go e to the e to the. So e to the 3.912 is about 50. Because e to the natural log cancel out, boop, we just get 50. E to the, that's it. Here, e to the negative 5 is about 0.0067. To undo that, or to put it in natural log form, I would just take the natural log of each side. Notice, I am not multiplying by ln. I am using the natural log as a function, kind of like a square root, like when you square root both sides. You don't multiply by a radical, you square root both sides. So here I am taking the natural logarithm of both sides. Natural log of e to the negative 5 just gives me negative 5, because those are inverses, they cancel out. And then I get natural log of 0.0067. So you can check those in your calculator. Type in e to the 3.912, you get about 50, won't be exact. Type in natural log of 0.0067, you'll get about negative 5, not quite, it'll be close though. Okay, now we're going to talk a little bit about graphing some logarithmic functions. So we're going to talk about graphing a basic one, and then a transformation, and that'll be it for the video. Sorry, all this talking. Gotta drink a little water so I can continue talking. All right, so in general, for any logarithm, if you have g of x or y equals log base b of x, and you want to graph this, you can always create this table. And this is for a non-transformed logarithm. So here we've got 0, 1, 2, 3, negative 1, negative 2. So the logarithm is being the inverse of the exponential. We can think of it in a similar way that we think about graphing a square root. When we want to graph a square root, right? If I'm going to graph a square root, like square root x, I want to pick numbers like 0, 1, 4, 9, 16, because the square root of each of those numbers, right, is a nice number. Right, square root of 9 is 3. If I go like square root of 5, I get this weird irrational number, which I'd rather not approximate on a graph. So what we got to do here is we got to pick nice x numbers that when I take the logarithm base b of that number, I get a nice answer. So we know from what we did earlier that b to the 0 or 1 always gives us 0. So here we always have an x-intercept at 1, 0. Remember, this is a non-transformed. No transformations, just the basic parent function log base b of x, right? Remember, b to the 0 is just 1. Now, if I put b in here, log base b of b is 1, because remember, this is b to the 1. And remember, the answer, the y value from a logarithm, is the exponent from the x number. So b to the 2, this exponent, b squared, the logarithm of b squared is going to be 2. The logarithm of b to the 3rd is going to be 3. So here, if I want to go negative, I got to go b to the negative 1, which remember is 1 over b. For negative 2 is my y, I'm going to go b to the negative 2, which is 1 over b squared. So, notice b is a positive number because it's the base of the logarithm. We don't ever do that with negatives. We never put a negative in the base, that'd be weird. Like, yeah, we'll talk about that later. It's kind of fun to think about, but we don't do it. So, if I take a positive and continue multiplying it, positive, positive, take a positive and continue dividing it, positive, positive. So our domain is always positive, right? The domain is 0 to infinity for all these logarithm functions. The range, as these numbers continue getting closer and closer to 0, the y values get bigger and bigger, or sorry, more and more negative. So negative infinity. These y values will continue increasing. They're going to increase incredibly slowly for a b value that is greater than 1, but they will increase. So it will go all the way to infinity. There's no stopping it. It's just going to take forever to get to whatever number you want it to. Like to get to 100, whew, that'd take forever. Right, if I had like log base 10 of x and I want it to be 100, I'd have to go 10 to the 100 to get that x number. 10 to the 100! That means I'm multiplying 10 times 10 times 10 100 times. It's a huge number. Sorry, we didn't need to go into that. And then also, because here, right, we're getting these numbers are getting more and more, sorry, they're getting closer and closer to 0. They're getting really, really, really small, but they're staying positive. We have a vertical asymptote at x equals 0. So let's go ahead and graph this for log base 3, and then we'll do a transformation of log base 3, and then we will call it GOOD, good. We'll call it good after that. All right, so we're going to graph h of x equals log base 3 of x. So we can just make a little table here. If we want, you don't need to, but I like to make a table. 1, 3, 9, because 9 is 3 squared. 27, because 27 is 3 to the 3. So when x is 1, the logarithm of log base 3 of 1 is going to be 0. Log base 3 of 3 is 1. Log base 3 of 9 is 2, because 3 squared is 9. Log base 3 of 27 is 3, because 3 to the 3rd is 27. Right, notice these x numbers are getting really large. Right, 81 for 4. Right, they're getting really large as y is getting large in a very slow manner. Now, if I want some negatives here, like negative 1, negative 2, I got to go 1/3, 3 to the negative 1, 1/9, 3 to the negative 2. So to sketch this graph, I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Not going to go out to 27. That's too big of a number for my liking. And 1, 2, 3, 1, 2, 3, negative 1, negative 2, negative 3. So I'm going to put these points on there. I've got my y-intercept at 1, 0. I misspoke. X-intercept. Not y-intercept, x-intercept. There is no y-intercept because we have an asymptote at the y-axis where x equals 0. And then 3, 1, 9, 2. We get a graph that looks like this. It's always increasing, but ever so slowly, like so slowly. Like it won't hit 3 until all the way out here like 27. but it's still increasing. And then as I go closer to the y-axis, right? I go like -1, -2, and I approach the x-axis, but it goes like almost straight down. There's still a curve to it. There's an ever-changing slope. It's getting steeper and steeper and steeper. It's not a straight line, but it's getting arbitrarily close to x equals 0, but never quite getting there. So we have this asymptote at x equals 0. Okay, so let's go ahead and graph f of x equals -4 log base 3 of x minus 2. So in order to graph this, we're going to look at the transformations. We know we've got our parent function of log base 3 of x. So I'm going to apply the transformations here. So we have a reflection in the x-axis. It's going to go like this to like that now. We have a vertical stretch by 4, and then we have it shifted right 3, right? Okay, so the negative is the reflection, the multiply by 4 is our vertical stretch by 4, the right 2 is because if I put positive 2 in here, 2 minus 2 is 0, and we always pick like what number do we need to make the inside 0 here, right? So we want our starting point. So what this is going to do, oh, that looks like a 3, my bad, that should be a 2, right, 2, is this is going to make it so that we have a graph that looks like this instead of this, and it's going to be stretched by a factor of 4, so it's going to be a little steeper, it's going to be growing a little faster, and the right 2 is going to move our vertical asymptote, which used to be at x equals 0. That's our vertical asymptote. Now the vertical asymptote is at x equals 2. So if I want to sketch in this graph, I'm going to go 1, 2, and I'm going to immediately draw my asymptote. So asymptote here, let's do it in purple. So this is 2. And we always use a dashed line to represent an asymptote. Now, I'm going to graph this log base 3 from the asymptote, pretending this asymptote is this this y-axis. But everything I do from this asymptote, I'm going to multiply the y number by a -4. That's going to give me my reflection and my stretch by 4. So normally, I'm 1 to the right of the asymptote. I'm still at 0 for my y. 0 times -4 is still 0. So here, I have the point 3, 0. Notice, if I put 3 in here, 3 minus 2 is 1. Log base 3 of 1 is 0. -4 times 0 is 0. Boom, got it. All right, if I go 1, 2, 3 to the right, I go up 1. So I'm going to go 1, 2, 3 to the right. So 2, 3, 4, 5. This is at 5. Normally I'd go up 1. 1 times -4 is -4. So I'm going to go down 1, 2, 3, 4. So I have the point 5, -4. Right, if I put 5 in here, 5 minus 2 is 3. Log base 3 of 3 is 1. -4 times 1 is, whoop, -4. All right, next, if I go from the asymptote 9 to the right, I go up 2. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So from 2, that's going to be 11. So 9 to the right of the asymptote. Normally I go up 2. 2 times -4 equals -8. So I'm going to go down 8. So 4, 5, 6, 7, 8. So this is the point 11, -8. And I get this shape of the curve here. Right, notice if I put 11 in here, 11 minus 2 is 9. Log base 3 of 9 is 2. -4 times 2 is -8. Right, those points line up. they log up. And then here, as we go close to the asymptote, we shoot down. That reflection is going to make it shoot up. You don't have to worry about being as exact, but like at a half away, we're going to be at 4 instead of at -1, and just make it go up along that asymptote there. All right, that is it. Hopefully that helped. Hopefully you enjoyed the British accent joke. And good luck on the homework. Remember, I got office hours. You got extra questions. Have a wonderful day.